Now we'll be moving on into how to create your own deep learning model inside Python using a module which we call Keras, which is itself a part of TensorFlow. So the way how you create a model is through Keras.sequential, which creates a neural network as stack of layers. And we could define a very simple one layer linear model accepting three input features and producing a single output like so. So we import keras through TensorFlow and we import layers through the imported keras, and we create a model using keras.sequential, creating one layer which has a one unit of neuron and an input of 3 units. So we will play that and produce the model. So this is how the one layer model will look like, which is essentially going to be the rate layer only. So we're creating one layer with one neuron, which outputs one single thing using three inputs. So one, two, three, going through an intermediary layer, one neuron, and then producing an output. And then this blue layer is a completely separate independent layer that produces a different output given the same inputs. And when we combine those two together, we have what we call a dense layer. So a dense layer is essentially a collection of some linear units given a common set of inputs. And you can think of each layer as performing some kind of relatively simple transformation. And so that will essentially mean the input multiplied by the weight of that input between that input and the intermediary neuron producing a single output, which will be then summed up with the other multiplications. So in a well-trained neural network, each layer is itself a simple transformation that gives a little bit part of the solution. Next, we'll be moving on to the activation function. So it turns out, when we have these two dense layers with nothing in between, it's really no better than us having a single dense layer by itself. Dense layers by themselves, they don't produce very valuable information. So we need something that is non-linear. And to demonstrate why this is, look at this graph. So we have this deep learning protocol that has a layer with a bunch of neurons that produces a classification whether the input is either A or B, a cat or dog. So what a linear unit transformation does is that it gives you a clean cut through the input to classify whether it's a cat or a dog. So you can think of, after putting all of the images of the cats and dogs into this deep learning algorithm, it will produce a single line that will cut through the inputs to tell whether this is a cat or a dog. And this is good if your inputs are able to be cleanly cut between each other. But what if the input is a bit more complex, such as this? You have a bunch of inputs, which is a picture of either a cat or a dog, and the boundary between them isn't a clean cut line that you can just create a line between the set of inputs. So what you need is something that is non-linear, something that can basically bend itself. So what we need is a nonlinear relationship activation function. And one of the most common activation functions that we use is what we call a rectifier function. So a rectifier is essentially taking the maximum of zero and the input. So in other words, if the input is ever negative, we will make it zero. If it's positive, don't do anything, just output whatever you have. So in essence, this is what the rectifier function will look like. It is rectified to zero. The minimum must always be zero. And when we attach the rectifier to a linear unit, we have what we call a rectified linear unit, or ReLU.